Good evening, everyone. Today in this session, we'll be starting with the wave optics, right? And there are majorly three main topics in the wave optics. One is the Huygens principle, right? With the help of Huygens principle, we can prove the laws of reflection and laws of refraction as well, right? Then we have the interference, right? And related to the interference, we have the important experiment, that's the Young's double slit experiment, right? That's YDSE. And then we have the last topic, that will be the diffraction, right? So these are three major topics with respect to the wave optics, right? We'll be starting with the Huygens wave theory, right? So according to Huygens, he gave a theory what we call as a Huygens principle, right? He said that light travels in the form of a wavefronts, right? He said light travels in the form of a wavefronts, right? Now the question is that what are these wavefronts, right? Now you can see here there's a source of light, right? This is the source of light, and in this direction the light is traveling, right? So Huygens said that wavefront is nothing, it's the locus of all particles, right, which are vibrating in the same phase, right? The locus of all particles which are vibrating in the same phase, right? It means that the particle will reach their maxima at the same time, minima at the same time, and at the zero position at the same time, or they will gain the maximum speed at the same time, minimum speed at the same time. So that's what do we mean by the by the particles in the same phase, right? So the Huygens said that the light actually travels in the form of wavefronts, and wavefronts are the region or the locus of space, locus of particles in space, right, which are vibrating in same phase, right? And he said that light travels in the form of a wavefront in a medium, right? When light travels in a medium, then the particles of medium start vibrating, and consequently, a disturbance is created in the medium. According to Huygens principle, light requires a medium, right, to travel, right? But the thing is that, Huygens said that when light travels in a medium, then the particles of medium start vibrating, and consequently, a disturbance is created in the medium, right? So every point on the wavefront becomes the source of secondary wavelight. So these are the particles, right, which are in the same phase, or we can say this is the wavefront, right? This is nothing. This is nothing. This is the wavefront, right? These are the particles which are in the same phase, or we can say this is nothing. This is the locus of particles which are in the same phase, and we call it as wavefront, right? Now, each and every particle on this wavefront will become a source of the secondary waves, right? This will become the source of secondary wavefront or the secondary waves, right? So how we can actually draw the secondary wavelets, right? Now, these are the particles, or these are the points. We'll draw. We will draw a sphere around this center, right? Around the symmetrically around this, taking this as center, symmetrically drawing a sphere around it, right? On each and every point, right? Then the common tangent, which then the common tangent to these spheres, right, creates an envelope, right? And this envelope we call as secondary wavefront, right? This envelope we call as secondary wavefront according to Huygens principle, right? Secondary wavefront, right? Secondary wavefront according to Huygens principle. So Huygens principle says that the source for the secondary wavefront is nothing, it's the previous wavefronts or the particles on the previous wavefront, right? We will draw a sphere symmetrically on those parts, keeping those particles at the center of the sphere. Symmetrically, we'll be drawing a sphere. Then the common tangent to these spheres will represent a new wavefront, right? That we call as secondary wavefront. And the direction along which the secondary wavefronts move will be the direction of the speed, or will be the direction of the light, right? So these are the basic principles given by Huygens, right? So according to Huygens, light travels in the form of a wavefront, and wavefront is the locus of all particles which are vibrating in the same phase, right? And the secondary wavelets are drawn, secondary wavefronts are drawn by drawing the spheres, taking center of the particles of the wavefront as center, right? And drawing the symmetric spheres, then the common tangent to these spheres will be the secondary wavefront, right? That's what the Huygens principle says, right? Now the intensity of these light, now these wavefronts can be of many types, right? Commonly we have three types of wavefronts. One is spherical wavefront, right? We have spherical wavefront, we have cylindrical wavefront, and plane wavefront, right? The source for the spherical wavefront is a point source, right? Point particle, right? The point particle is the source of spherical wavefronts, right? The point particle will be the source of spherical wavefronts, right? The source for the spherical wavefronts will be the point source, right? You can see here there's a point source, and it sends a spherical wavefronts, right? and the direction of this is the direction, or we can say the perpendicular to the wavefront, actually gives the direction of the speed of direction of the flow of light, or direction of the flow of energy, right? And we know that intensity at any point is actually inversely proportional to the area, right? Since these wavefronts are these wavefronts intensity is inversely proportional to the area A, right? Area A, these wavefronts are spherical in nature, and the area of sphere is nothing. It's actually 1 by 4 pi r square, right? That's 4 pi r square. It means intensity in case of spherical wavefronts is varies as 1 by r square, right? It varies as 1 by r square. If intensity varies as 1 by r square, then the amplitude will vary as under root of intensity, right? Under root of intensity, or amplitude varies 1 by r, right? It will vary as 1 by r. So this is how the amplitude varies in case of spherical wavefronts, right? Now, similarly for the cylindrical wavefronts, right? For the cylindrical wavefronts, the source is actually a line source, right? Line is a source for the spherical wavefronts. For the cylindrical wavefronts, right? For the cylindrical wavefronts, linear source is actually a source of cylindrical wavefronts, right? And then we know that for intensity is inversely proportional to the area once again, right? And for cylinder, it's the area of covered surface area for the cylinder is 2 pi r h, right? It means this intensity will be inversely proportional to r, right? Or the amplitude in case of cylindrical wavefront will be directly proportional to 1 by root of r, right? 1 by root of r in case of cylindrical wavefronts, right? Similarly, for plane wavefronts, the source is actually extended source, right? Placed at infinity or at large distance, then the wavefronts from that source will be the plane wavefronts, right? And the intensity will be proportional to the r to the power 0. It means the intensity of the plane wavefronts or extended plane wavefronts is actually a constant. It's independent of the distance, right? So the amplitude will also be a constant, and it will be independent of distance. So the direction of the flow of light actually is perpendicular to the wavefronts, right? Now let's try to prove certain laws, right? Laws of reflection, laws of refraction, using the Huygens principle, right? Now you can see there are two reflected rays. One is striking at A, another is striking at B dash position, right? These are two reflected rays, right? The angle of incidence is I, right? Angle of incidence here is I, and this angle here is this angle here will also be, they are parallel, right? They are parallel to each other. This is I, this is I, then this angle here, let's suppose, is R, and this angle will also be equal to R, right? Now what we'll do is that we will try to calculate the distance covered by this, let's suppose in time, the in time t, the ray of light reaches this position, right? This wavefront reach this position after reflection. Then the distance a dash will be nothing. It will be the speed of light in this medium, that will be v1, and multiplied with the time t. Similarly, the bb dash will be here, that will be equal to the speed of light, that's v1, multiplied with the time t, right? That will be time t. Now in triangle ABB dash, in triangle ABB dash, if we calculate this, if we calculate the value of sine of I, right? Sine of I. Now we have constructed a normal, right, perpendicular to these lines, to these incident rays. This is another perpendicular which is constructed perpendicular to the reflected ray, right? First reflected ray. Now you can see this triangle ABB dash. We can calculate the sine I. The sine I will be nothing. The sine I has to be actually it will be equal to sine I. It will be perpendicular upon hypotenuse, right? And the perpendicular here is PB dash, right, upon AB dash, right? And similarly, we will have sine R equal to sine R, it will be AB, right? Sine R, it will be AA dash, right? It will be AA dash, AA dash, AA dash upon uh, AB dash, right? AB dash, yes. It will be AA dash upon AB dash. Now, you can see here, AA dash is equal to V1T, and BB dash, that's the length, that's equal to V1T, right? It means from here, AA dash has to be equal to BB dash, right? Has to be equal to BB dash, and each will be equal to V1T. Now, let's take the ratio of sine I and sine R, right? Sine I upon sine R, here in this case, will be equal to, it will be equal to sine I is BB dash, right, upon AB dash, right? And AA dash is equal to BB dash. We can write here it as BB dash upon AB dash, right? AB dash. Now it will get cancelled. We'll be left with 1 here, right? So from here we get this value of sine I, that will be equal to sine of r, right? That equal to sine r. Or we can say angle I is equal to angle r, right? This is nothing. This is the law of reflection. Law of reflection. So this is the proof of law of reflection using the Huygens principle, right? So according to Huygens principle, we can actually prove the laws of reflection, right? Where angle of incidence is always equal to angle of reflection. Now let's try to prove the law of refraction by Huygens wave theory, right? By Huygens wave theory. Now you can see here once again the distance. We can see here that there are two light rays, right? One is entering into the medium. There is a refraction, right? Here angle of incidence is I, right? Is a refraction where the angle of refraction is equal to r, right? Angle of refraction is equal to r, and v1 and v2 are the two speeds of this light in two different mediums. This is the outside medium, this is the inside medium, right? The speed of light in first medium is v1 and the speed of light in second medium is v2, right? Now uh, now talking about the length traveled by this refracted ray AA dash, right? AA dash. This AA dash length will be nothing. This will be equal to this has to be equal to speed in the second medium multiplied by the time, right? And similarly, BB dash will be equal to speed in the first medium, that's V1, because this BB dash is in the first medium, it will be V1 multiplied by T, right? Now once again, let's let's try to find this in triangle ABB dash, right? In triangle ABB dash, right? In triangle ABB dash. Sine of I will be nothing. Sine of I will be nothing. It will be equal to sine of I has to be equal to sine of I, that will be equal to a perpendicular, that's PB dash, right? PB dash upon hypotenuse, that's AB dash, right? That's AB dash, right? Similarly, we have to calculate in triangle A B dash A dash B, right? A dash B, right? A dash B. We'll calculate the sine of R, that will be equal to sine of R will be equal to A dash upon AB dash, right? AB dash. Now let's call this first and let's call this second. Now let's divide first and second, right? It will be sine I upon sine R, right? Sine I upon sine R, that will be equal to PB dash upon AB dash upon A dash divided by AB dash, right? Now AB dash and AB dash will get cancelled. We'll be left with BB dash upon AA dash, right? I can see BB dash is nothing, that's V1T, and AA dash is V2T, right? This T and T will get cancelled. It is nothing. It's actually nothing. It's equal to mu2 upon mu1, right? Mu2 upon mu1, right? This is mu2, this is mu1, right? This is mu1. So from here, we get that from here we get sine I upon sine R, nothing. That's equal to mu2 1, that's the refractive index of medium 1 with respect to medium 2, or we can say that mu1 sine I is equal to mu2 sine R, right? Mu2 sine I is equal mu1 sine I is equal to mu2 sine R. This is nothing. This is the proof of the law of reflection or Snell's law, right? According to Huygens theory, right? Snell's law. So from here, mu1 sine I is equal to mu2 sine R. This is the law of reflection or Snell's law, right? So this is how we can prove laws of refraction using the Huygens principle, right? Now let's talk about the interference, right? For the interference or for the sustained interference to take place, right? We should have a coherent sources, right? Let's discuss what are actually the coherent and incoherent sources, right? So we have two light sources. They are said to be coherent if they emit light waves of the same frequency and have a constant phase difference between them. The two light waves or the two light rays are said to be in phase when they have the same frequency, right? They are emitted from the same source, right? They have the same frequency, right? They have the same frequency and have a constant phase difference, right? So this is only possible if the source of the light for the same if the source for those light waves is actually same, right? Then only it's possible to have a coherent source, right? They will have the same frequency because frequency of light depends upon the source, right? Now, and they can have a constant phase difference as well, right? So the only possible only possible condition is that these light rays should should be from a common source, right? Then only they will have the same frequency and they will be having a constant phase difference between them. You can see in this picture, this is the bulb here, right? This is the bulb here, right? And from this bulb actually this the light waves from this bulb actually enter the slit 1, right, S1. And after this entering the slit S, right, this becomes the source of the light waves, right? And then what happens is that the division of the wavefronts takes place between S1 and S2, right? But they are from the same source, right? They are from the same source. They will have the same frequency with a constant phase difference, or we can say these two light waves are actually coherent in nature, right? They are coherent light waves. Coherent light waves, or S1 and S2 now will become coherent sources, right? These are nothing, these are coherent sources. They are coherent sources of light. They have the same frequency and constant phase difference between them. While any light wave which do not have the same frequency or constant phase difference between them, right? Any light wave which do not have the same frequency or the phase difference between them varies, right? They are called as incoherent source. They are not coherent, right? They will be called as incoherent sources of light, right? If their phase difference changes with time, right? So two independent monochromatic sources of same frequency are incoherent because we know that atoms cannot emit light waves in same phase, and these sources are said to be incoherent, right? So there will always be a phase difference between the light emitted by two different sources, right? Because the transition it's not possible, or it's not always possible to have a same type of transition in atoms, right? So the frequency of the photons or the frequency of the light emitted by the atoms will vary, right? From transition to transition. So it's not possible to have. So those waves will be called as incoherent waves, right? So generally we have the incoherent sources, right? We have the incoherent sources of light, right? Now let's talk about the interference, right? The interference is nothing when the two waves emitted from the coherent sources, right, propagating in the same direction and they are superposed over one another, right? And what happens is that the redistribution of the energy takes place, right, in the space. And this redistribution of energy in the space, when the two waves of from the coherent sources actually superpose on each other, this is what we call as interference, right? And in this interference, actually redistribution of energy takes place, or we can say interference is based on law of conservation of energy, or it's based on energy conservation principle, right? The total energy of the waves remains constant, right? Total energy remains constant, only the redistribution of the energy takes place, right? So superposition of two light waves, right, from the coherent source, or they should be in the same phase or having the same frequency, right, in this space, that's what we call as interference, right? So you can see here there are two waves, wave 1 and wave 2. They are superposed on each other, and superposition of these two waves gives us the single resultant wave, right? This is what we call as the superposition of the two waves, right? Now let's suppose if we have two waves, right, they can interfere in two ways. Let's suppose two waves interfere in this manner, right, such that if they interfere with each other, then the magnitude of the amplitude of the resultant wave is larger than the magnitude of the amplitude of individual waves, right? Then in that case we say that the interference is actually constructive interference, right? constructive interference constructive interference. And you can see this is the light wave, right? This is another light wave, right? Now the interference takes place in such a way so that the resultant actually becomes a dark light, right? It's a dark. It gives us a dark spot, right? It means that intensity, the total intensity gets minimum, right? The total intensity or the total amplitude of the resultant wave becomes minimum, right? And this type of interference we call as destructive interference. So there are two types of interferences possible: constructive and destructive interference, right? Now, in case of, or we can say if we have two bright sources, right, when they interfere constructively, they give a more bright light. Or if we have two bright sources, if they interfere destructively, then the intensity of the resultant light actually decreases, right? Now let's try to see how we can calculate the intensity of two different light sources, right, upon interference. Now let's see there are two light sources, coherent light sources, each of amplitude one of amplitude A1, another of amplitude A2, right? And the phase difference between these two light waves is actually phi, which is a constant phase difference, right? So phi is the phase difference between them, right? Phi is nothing. Phi is the phase difference between them. Phase difference between the two lights, or the between the two waves, right? Between the two waves, right? So the resultant of these two, or the resultant amplitude of these two waves will be given as, it will be A is equal to, it will be under root of, it will be this in the same way, right? If we represent amplitude of one wave with this phasor, right, phasor A1, and the amplitude of second wave with the phasor A2, then the phase difference between them is pi. Then the vector addition of the amplitudes of these two waves will be nothing. It will be under root of A1 square plus A2 square, right, plus twice A1 A2 cos of phi, right? So this will be the resultant amplitude of the resultant wave, right? This will be the amplitude of the resultant wave, right? And similarly, this the phase, or we can say the total phase of this resultant wave will be that by tan of theta, right? Tan of theta, that will be equal to A2 sine of phi, right? A2 sine of phi, A2 sine of phi upon A1 plus A2 cos of phi, right? A2 cos of phi. This is how we can calculate the resultant phase of this resultant wave with respect to this phasor diagram, right? A2 cos of phi. So this will be the resultant phase. Theta will be the resultant phase, right? So theta will be here tan inverse of A2 sine of phi, right? A2 sine of phi upon A1 A plus A2 cos of phi, right? A2 cos of phi. Now talking about the resultant intensity, right? Now talking about the resultant intensity, we know that intensity is proportional to amplitude square, right? It's proportional to amplitude square, right? So therefore, the resultant intensity will be nothing. It will be equal to A1 square. We can replace it with I1, right? So the resultant amplitude will be I1 plus I2, right? Plus 2 times under root of I1, root of I2, cos of phi, right? So this will be the resultant amplitude or a resultant intensity of the two waves, right? So the resultant intensity of the two waves will be nothing. It will be I1 plus I2 plus twice root I1 root I2 cos of phi. So this is nothing. This is the resultant intensity, right? So this resultant intensity will depend upon this phi. This is nothing. This is the phase difference, right? This is nothing. This is the phase difference. Phase difference, right? Now let's suppose if a phase difference if the phase difference between these light sources is 0 degree, right? 0 degree phase difference, right? Then the resultant intensity here in this case will be equal to I1 plus I2 plus twice root I1 root I2, right? It means the intensity here will be maximum, or we can write this maximum intensity here, that will be under root of I1 plus I2 whole square, right? So this will be the maximum intensity in case of constructive interference, right? Maximum intensity, right? Similarly, if we have the destructive interference, right? In that case, phi will be equal to, let's suppose pi, right? Pi is the uh, phase difference between the two light sources, right? In that case, the resultant intensity will be equal to I, that will be equal to under root of I1 minus under root of I2 whole square, right? So this will be the minimum intensity upon destructive interference between the two light sources, right? Now, condition for sustained interference, right? What are the conditions to sustain the interference between two light waves, right? The two sources should be actually coherent in nature, right? For the sustained interference to occur, the two sources should be coherent in nature. The separation between two coherent sources should be appreciably small, right? There should be small separation between the two sources of light, right? and the distance of the screen from the two sources should be large, right? So if there is a source on which we're actually projecting the interference pattern, right? Then the distance between screen and the two sources should be very large so that we can actually sustain the interference, right? And for good contrast between, or we can say the good separation between the maxima and minima, the amplitude of two interfering waves should be equal as nearly as possible, right? So if the amplitude of the two waves are same, then it's possible to have more sustained interference, right? So these are some of the conditions, right? We should take care in experiments, right? So that the sustained interference can be obtained, right? Well, let's focus on this experiment. That's the Young's double slit experiment, right? Let's try to calculate. Let's try to calculate the different conditions for this experiment, right? Now you can see here Young's double slit experiment is based on the interference pattern, right? Where the constructive and the destructive interference takes place between two light sources, right? Now you can see here there is a common source S, right? There is a common source S for the light. From this common source, the light is emitted or the wave is emitted, and because of uh, because of these two slits, these light waves get divided into two sources, S1 and S2, right? And the slit separation between S1 and S2 is D, right? D is the slit separation between them, right? And let's suppose this angle here is theta and this angle is also equal to theta, right? Now we know that a destructive or the constructive interference to occur, it will depend upon the phase difference between the two waves or the path difference between the two waves, right? Now you can see here, let's suppose S wave from the S1 strikes the screen at point P and the wave from S2 also strikes the point P right on the screen, and interference occurs, right? Interference occurs, right? So we can see here there's a path difference, right? Path difference between the two waves, right? So there will be some phase difference as well between the two waves, right? You can see here the phase difference or the path difference delta x will be equal to, it will be S2P, right? Because this is the larger length, right? Minus S1P, right? Minus S1P. Or we can say that if this angle is theta, then the component of this slit separation along this S2P will be nothing. It will be equal to S2M, right? S2M. That's actually the path difference, right? S2M, right? And this S2M is nothing. It's equal to T sine theta, right? It's equal to T sine theta. So delta x is nothing. It's equal to T sine theta, right? Now this path length will actually decide whether the interference will be the constructive interference, whether it will be a destructive interference, or the bright fringe will occur on the screen or the dark fringe will occur on the screen, right? So d sine theta is equal to delta x, right? D sine theta, if d sine theta is equal to delta x, then condition, let's suppose this theta is small, right? Theta is small. If the theta is small, right? If theta is small, right? Theta is small, then we can approximate sine theta to tan theta, right? Sine theta to tan theta, right? Now this delta x nothing, it's the path length, right? Path difference, that's t sine theta, and we can approximate it to t tan theta, right? T tan theta, right? Now this tan theta is nothing. Let's suppose at a distance of y, vertical distance of y from the center of the screen, the spot occurs, right? Or the interference occurs, right? So this tan theta will be nothing. The separation between the slit and the screen is capital D. So d tan theta will be nothing. It will be d times yn upon d, right? Yn upon d. So we can say that path length or the path difference is nothing. It's y small d upon capital D, right? Where capital D is nothing, it's the separation between slit and screen, right? It's separation between slit and screen, right? Slit and screen. It's the separation between slit and screen, right? And D is nothing, it's the slit width. Small d is nothing, it's the slit width. Small d is actually slit width. So YD upon D is the path length or the path separation, or we can say path difference between the two waves, right? Now this path difference will decide whether the interference will be constructive or destructive in nature, right? Let's see, for the constructive interference, the bright fringe will occur, right? And for the destructive interference, the dark fringe will occur, right? So you can see here the delta x was equal to delta x was equal to delta x was equal to y t upon t, right? Now let's suppose for the constructive interference or for the bright fringe to occur, the condition for uh, path length should be equal to n lambda, right? It means delta x should be equal to n lambda for the uh, constructive interference, right? For the constructive interference to occur, the path difference should be n lambda, right? Or we can say in the position of nth bright fringe will be nothing. It will be n lambda capital D upon the small d, where small d is the slit separation, right? Capital D is the separation between the screen and the slit, right? Or we can say nth separation or nth maxima occurs, right? Nth maxima occurs, right? At a position from the center of the screen, that's given by n lambda d upon d, right? N lambda d upon d. So the first bright fringe actually occurs. The bright fringe occurs at the central position. We know that at central position, you can see this will be the fringe pattern, right? This is how the bright fringes will occur, right? At the central position, the at the central position, the path difference between the two ways is actually zero, right? In that condition, the bright spot will occur at the center of the screen, right? Then the first maxima will occur at lambda d upon d, and the second maxima will occur at 2 lambda d upon d, and similarly, the third maxima will occur at 3 lambda d from the center, right? So the position of nth bright fringe, right? Position of nth bright fringe will be equal to n lambda d upon d, right? So for the first bright fringe, it will be 1 lambda d upon d, and second 2 lambda d upon d, and the central bright fringe will occur at the center of the screen, right? Because the path length or the path difference between the two waves is equal to 0 at the center, right? In that case, the bright spot will occur at the center of this screen, right? Similarly, there will be destructive interference also. So this is a condition of constructive interference where the bright fringe will occur, right? For the destructive interference, the dark fringe will occur or the minima will occur, right? So the condition for minima to occur is that this delta x in that case should be equal to, in that case, delta x should be equal to 2n minus 1 lambda upon 2, right? If this is the condition, right? If this is the condition, then in that case, the minima will occur or the dark fringe will occur, right? The position of this nth dark fringe will be nothing. It will be given by 2n minus 1 into lambda upon 2, right? Multiplied by this factor d and upon d, right? So this is the condition with the help of which we can actually find the nth minima, right? Nth minima, right? So at the center there is a maxima always, right? In case of single slit Young's double slit experiment, right? Now you can see here the position of the nth minima is 2n minus 1 lambda d upon 2d, right? Lambda d upon 2d. Now the separation between these fringes, right? Or we can say fringe width, right? It's nothing, it's the separation between two consecutive fringes, right? That's what we call as fringe width, right? So you can see here for both minima as well as maxima, the fringe width will be nothing. Let's suppose between second maxima and first minima. Second maxima y2 occurs as 2 lambda d upon d, right? 2 lambda d upon d, right? And the first maxima occurs at lambda d upon d. The separation between them will be nothing. That's fringe width beta, right? That will be 2 lambda d upon d minus lambda d upon d, right? So that will be equal to fringe width, that's equal to lambda capital D upon small d, right? So this is nothing, this is the condition for the, this is nothing, this is the fringe width, right? This is the fringe width, right? So the fringe width, whether it will be a minima or maxima or dark spot or the bright spot, right? Fringe width for both the cases will be same, it will not change, right? It will be same for both dark fringe as well as bright fringe, right? It will be equal to lambda d upon d, right? So now let's move on to the diffraction, right? let's quickly discuss the diffraction, right? So diffraction is nothing, it's actually the bending of light rays, right? Bending of light from sharp edges of an opaque obstacle, right? Or aperture, right? And spreading in the geometrical shadow region. That's what we define as the diffraction of light or deviation of light from its rectilinear propagation tendency, right? That's what we call as diffraction, right? The phenomena of diffraction was actually discovered by Grimaldi, right? It was discovered first by Grimaldi, right? Then there were various experiments on the diffraction as well, right? So actually, it's the what we is it's actually the spreading, right? Spreading of the light at sharp edges of an opaque obstacle, right? Now we can further move, right, to see the conditions of diffraction, right? The conditions of diffraction are that size of obstacle or aperture should be comparable to the wavelength, right? If the size of the object is comparable to the wavelength, then the wave behavior will be shown by the light wave, right? Or we can say the diffraction behavior will be shown by the light wave, right? Or the diffraction will occur, or the spreading of the light around that obstacle or around that object, right? Whose wavelength is very comparable to the wavelength of the light. And the diffraction is going to occur, right? If size of object is much larger than wavelength, then diffraction is not observable, right? And practically, it is said that when size of aperture is greater than 50 times the wavelength, right? The obstacle or the aperture does not show the diffraction, right? So it's very mandatory, right? That the wavelength of light should be comparable to the size of the object to observe the diffraction patterns, right? To observe the diffraction pattern, right? Let's talk about the Fraunhofer diffraction, right? In Fraunhofer diffraction, the object is actually at large distances, right? Large distances, right? Now, the condition for the diffraction to occur is that, right? So at this spot, the two light waves, right? The two light waves interfere at this spot, right? Or the spreading of light rays takes place around the single aperture or single slit, right? So that spreading of this light is actually seen on the screen, right? And this spreading of this light is what we call as the diffraction, right? And the pattern obtained is called as diffraction pattern, right? So the condition for the diffraction pattern to occur, right? There are once again the bright fringes and the dark fringes, or we can say maximas and the minimas that occur in the diffraction pattern as well, right? So the condition for the diffraction pattern to occur on this, or we can say the constructive pattern or the destructive pattern, constructive diffraction pattern or the destructive diffraction pattern occur on the screen, right? Or the bright fringe or the dark fringe to occur on the screen, right? So the condition is that if the slit width is between this end to this end, if slit separation here is, or the length of this slit is equal to A, right? Or we can say the length of this aperture, right? The length of this aperture from A to B, right? From A to B is actually A, right? The length of this aperture should be very much comparable to the wavelength of the wave, right? Then in that case, A sin theta will be equal to the, that will be equal to delta x. That's nothing, that's the part difference, right? Part difference. So A sin theta will be part difference. So A is nothing, it's the size of aperture, right? Size of aperture. Size of aperture or slit, you can say. Size of aperture or slit. Or slit, right? Now for the bright fringes to occur, right? Or the dark fringe to occur, the condition for this part difference should be, in case of diffraction pattern to obtain Fraunhofer diffraction pattern to obtain, A sin theta should be equal to n lambda, right? It should be equal to n lambda for the bright dark fringe, right? For the dark fringe to occur, right? For the dark fringe. For the dark fringe to occur, A sin theta should be equal to n lambda, right? Or we can say the phase difference delta phi should be equal to 2n pi, right? It should be 2n pi, right? It should be equal to 2n pi. Phase difference between the two waves should be 2n pi for the dark pattern to occur or the dark fringe to occur, or we can say the minima to occur on this screen, right? Similarly, the condition for maxima to occur, right? On the screen, right? Condition for maxima to occur or bright fringe to occur is nothing that A sin theta should be equal to 2n plus 1 lambda upon 2, right? This is the condition for bright fringe or maxima, right? This is the condition for bright fringe or the maxima, right? And we know that sine theta is approximately can be treated as equal to tan of theta here in this condition, right? In this way, we can write tan theta equal to, that's nothing, that's y upon d, right? That's equal to y upon d, right? Y upon d. If theta is very small, then tan of theta will be equal to theta, right? Equal to theta, right? Or we can say the angular separation theta here. The angular separation of theta here will be nothing. That will be equal to, theta will be here equal to lambda upon a, right? Lambda upon a. And central, for the central bright, right? Central bright, the angular separation theta will be actually, if this is theta, right? This also has to be equal to theta. In that condition, this angular separation will be 2s lambda upon a, right? This will be 2s lambda upon a. So 2 lambda upon a will be the separation for the central bright, and for other fringes, be it dark or bright, the angular separation will be lambda upon a, right? For the bright fringe, right? Lambda upon a. This will be the angular separation, right? So that's it for today, right? In the next lecture, we'll be discussing some of the questions related to wave optics, related to YDSE experiment, diffraction, and Huygens principle, right? That will be done in the next lecture, right? We'll stop here. Till then, take care and goodbye.